we're interested in the change in internal energy for various experimental constraints. And so one constraint is the process be done reversibly. Well, then du is equal to dq reversible plus dw reversible, which is minus p dv. Because p is equal to p external for a reversible process. And we can write that. We could have isolated. Suppose we're looking at the system isolated from the outside world. Well, dq is equal to 0, and dw is equal to 0, because it's isolated. So that implies du is equal to 0. We could do an adiabatic process. Adiabatic means there's no heat transferred in or out of the system. We don't say anything about whether the system does work or has work done on it. Implicitly here, we're talking about a closed system, so there's no mass leaving the system. But if it's adiabatic, then dq is equal to 0. And for an adiabatic process, then du is equal to dw. Now, this is a point we want to be careful. Be careful. Suppose we are doing an adiabatic process. We can do it reversibly, or we can do it irreversibly. So suppose we do it irreversibly. Suppose we just remove stops and the system slams up against the other stops. Did no work. Does that mean du is 0? You bet it does not. So it's important to write this little thing on here. Du is equal to the reversible work, not just the work. You can have a process where you can measure an irreversible process where you could calculate the work done. It could be 0, it could be something else. But if it's not reversible, it's not du. And you will be invited to make that mistake on an exam, I'm sure. Well, for constant volume, dw is equal to 0. Why? How does it do, what is work? Well, it's PV work. If the volume doesn't change, there is no work. So in this case, du is equal to dq, and we put a little v on it to imply that the work, the change in internal energy is equal to the heat added at constant volume. Nothing reversible about it. It's now all we have to do is say we're going to add heat at constant volume.